better. It works better, though, if we crank up the heater all the way up. So this was at about, for the diesel device, about 18 volts. If we crank it to half of that, we actually see the inverse relationship.
And on the y-axis, that's the change in frequency?
This is the sensitivity.
It's the signal per...
Right. It's the signal, essentially. So the change of frequency, correct. And again, it's a negative change, right?
Right.
Yeah.
But bigger is better.
Bigger is better, correct. It's more sensitive if it's bigger.
Okay. Well.
Yeah. No, so then the interesting is, why is this happening? And so it turns out, we then analyze these things in the microscope. You can see here in the image, this is actually before the device was taken apart. The flow is coming in this way, and you can see that we see this discoloration, kind of like a crescent, on the side underneath the heater that's towards the flow. We remove the heater, and this is actually the outline of that, where the heater was located. The flow goes this way, and you can see this crescent of PM essentially here, right? So it seems like we're actually expelling all the particles in that air column, right? And so there are no particles left here to be deposited, which would actually explain this, right? This is why we have the high flow. But it also tells us that our thermophilic precipitator is more efficient than we thought, okay? It's about an order of magnitude more efficient. Okay. Now,
from the high heat?
This is right. This is from the high heat, but it doesn't actually matter because we did the calculation from both of them, right? So there are some interesting actually physics that we're investigating right now. It turns out when you shrink down the size of the channel, the mean free path between the heater and the particles gets smaller. So there are some secondary effects that actually amplify this the process. So that's one thing. The other thing is that we also probably get